Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am David Beams, and I will be your genial host and raconteur for this video. The good and learned and always dapper Mr. James was unavailable for this recording session, and I know that his absence will be a huge disappointment to our subscriber base, our loyal subscribers, all maybe 4 or 5 of you, but I promise we will see him again shortly in another video. What I wanted to do today was wrap up loose ends on the subject of sinusoidal oscillators and negative resistance after the second presentation in that series called Going Negative Part 2. I felt there were some things I needed to be recapitulated and re-emphasized. So hence this video, which is called Going Negative Part 3. And I also want to announce that under the aegis of the One Human Lifetime Project, that there will be resources concerning oscillator circuits that you can download and use, you can experiment with, you can work with them for your own personal interest. But I'll get to that. Remember, an LRC network with some initial energy, if the LRC network has a damping ratio less than 1, then an energized LRC network will exhibit a transient behavior that is a sinusoidal oscillation constrained within an exponential envelope. For a positive resistance, that exponential envelope is a decaying envelope. So the amplitude of the oscillations is continually decreasing. And as energy is removed from the LRC network by the resistance is dissipating energy. Eventually, the energy will run out and the oscillation will cease. If the resistance is infinite, an open circuit, conductance of 0, then we get a constant amplitude oscillation. In this case, what's happening is the initial energy that's present in the network at time t equals 0 has nowhere to go because neither a capacitor nor an inductor can dissipate energy. They can only store it. So without a means of removing energy from the network, it simply is transferred back and forth between inductive and capacitive storage modes, and the amplitude of the oscillation is constant. Then, if there's some way that we could make a negative conductance, what we commonly call a negative resistance, what we would find is an exponentially growing envelope. With these things in mind, let's look at what it takes to make a sinusoidal oscillator in an electronic circuit. We need to make a circuit that mimics an LRC network with an initial negative resistance. So the oscillation would begin and would grow, at least at first. Capacitance is usually made up of a physical component. The inductance can be a physical coil of wire, like was used in the Colpitt's oscillator, or it could be a synthetic inductance, as in the Wein-Bridge oscillator. Now, there are oscillator circuits like the so-called Pierce oscillator, which use a quartz crystal to act as the inductor. And the negative resistance, we can either derive a negative resistance from devices that intrinsically show negative conductance, like the gun diode and the tunnel diode, or we can use a synthetic negative resistance. And then finally, we need some sort of passive or active method to stabilize the amplitude. So as the oscillation builds, the negative conductance diminishes, and eventually the oscillator should reach some equilibrium where the negative conductance of the network exactly balances the positive conductance of any load that's attached to the circuit. Let's take a look at the Wein-Bridge oscillator. This is a simulation circuit implemented in LTSpice that allows us to do both a transient analysis to observe its behavior with respect to time, but it also allows us to measure the admittance of the circuit with capacitor C2 removed. Remember, in previous presentations, what we did was we pulled C2 out of the Wein-Bridge circuit and looked at the admittance at this node. This part of the circuit provides both a synthetic inductance and a synthetic conductance. And then this is the C of the LRC network. So we remove the capacitance and look at the remainder of the network and look at the synthetic inductance and synthetic conductance that were produced thereby. Okay. For transient analysis, here are the directives for how to carry it out. You set this capacitor C shunt to 1 picofarad, a small value that really makes it inconsequential. And you set this resistance RDS to 100 megohms, which makes it essentially an open circuit. Why are these components there? Well, they are used in the measurement of the admittance across C2. I'll get to that in a moment. But for transient analysis purposes, we don't want these components to be present in the circuit, so we make them both very small, or we make the capacitance very small and the inductance very, very large. We can't make the capacitance of C shunt 0. SPICE will not accept 0 value capacitors, and we cannot make the resistance infinite. You can't have an infinite value component in SPICE. Okay. Anyway, we enable the transient analysis and we disable the AC analysis by putting this semicolon in front of the analysis directive. And then when we run it, this is the behavior, and it shows the exponential increase in the envelope and then the amplitude stabilization. This behavior we've seen before in the Wein-Bridge oscillator. It's familiar. Okay, now about measuring the synthetic inductance and synthetic synthetic conductance and synthetic conductance and synthetic inductance. Should never have tried that. Okay, right. AC analysis. Okay, now what we do here is for AC analysis, we carry out the steps that are listed here. We set C shunt to a very large value, 1 farad. And notice that in SPICE, I don't put the F behind it. That makes it 1 femtofarad. So just a 1 gives you 1 farad. Why 1 farad? It's huge capacitance. Well, at 1 kilohertz, which is the frequency of oscillation and the frequency at which we will look at the synthetic inductance and conductance of the Wein-Bridge, the active Wein-Bridge network. At that frequency, a 1 farad capacitor is essentially a short circuit. So that removes C2 from the circuit without my either removing C2 or having to change its value. So also with RDS, if I leave RDS at 100 megohms, then I can do an AC analysis to measure the admittance across C2 as under the conditions of the oscillation when it first begins, that is before the oscillation amplitude builds and the diodes D1 and D2 begin conducting. This branch of the circuit is essentially not present. But If I change the value to a small value like 1 ohm, that mimics the behavior of the diodes being fully conducting. And that puts R4 in parallel with R3. That mimics the case of the oscillation being fully developed. Okay. And I can use the same startup impulse that was used to make sure that the transient simulation began and the oscillation developed. I can supply it with not only a pulse specification for startup purposes, but I can also make it an AC source of 1 volt. Why an AC source of 1 volt? Well, with an AC source of 1 volt, the current being delivered through this essentially a capacitive short circuit, makes the voltage at this node 1 volt. And the current that flows out of V start into that node is numerically equal to the admittance. So I can make a direct measurement of admittance by measuring the current flowing out of V start. Now, what's this other voltage source doing here? Well, this other voltage source is used as an ammeter. I'm going to measure the current flowing in this voltage source. Well, it's in series with V start. Aren't their currents the same? Yes, that's true, except that SPICE uses a definition of positive currents entering a device at its positive terminal and leaving at its negative terminal. So the current that's delivered by V start is actually computed in SPICE as it would be minus V start. But that same current would be flowing into this other voltage source at its positive terminal, leaving at its negative terminal. Simply put, the admittance that this source sees is measured directly by the current flowing through this 0 volt voltage source VIM. It's an old trick in SPICE analyses. In some of the very early implementations of SPICE, the only way to measure a branch current was to put a 0 volt voltage source in that branch and measure the current flowing through the voltage source. Okay, so to measure the conductance of this network with C2 removed, we do this AC analysis at 1 kilohertz, and we can compute the conductance as the magnitude of the current in VIM multiplied by the cosine of the phase angle of IVIM. And the susceptance is the magnitude of the current flowing in VIM times the sine of that phase angle. And when I run this analysis with RDS set to 100 megohms, the diode amplitude stabilization branch of the circuit being essentially disconnected. So this reflects the startup conditions of the oscillator. Here is the current flowing through the ammeter voltage source, and it's 68.8 microamperes at a phase of minus 95.5 degrees. The admittance is numerically equal to, or is equivalent to, a resistance of minus 152K in parallel with a synthetic inductance of 2.32 henries. And we have the synthetic inductance and a synthetic negative conductance. So if we then add C2 back to the circuit, we have an LRC network with a negative conductance, and oscillation begins, and it grows exponentially in amplitude until the diodes begin to conduct, and that amplitude stabilization branch comes into play. Under those circumstances, here's an AC analysis with RDS set equal to 1. Here is the current, which is numerically equal to the admittance. And now it's 56.63 microamps at a phase angle of minus 84.1 degrees. that looks to the voltage source as if it's connected to a parallel circuit of 172K positive and a synthetic inductance of 2.82 henries. You see now, positive conductance, we would no longer be able to sustain the amplitude of oscillation. I mean, the oscillation would eventually decay to zero. So you can see that under startup conditions, we had a negative conductance, but if the amplitude were to build sufficiently, we'd have a positive conductance, and the conditions for sustained oscillation would no longer be present. Okay, so let's take a look at another example of an LTSpice circuit that's been configured so we can also do admittance measurements. Here we have the Colpitts oscillator. Now, for transient analysis, this additional inductor, which I called L shunt, I've set it to 10 henries. This circuit's supposed to oscillate at a megahertz. And at a megahertz, 10 henries has a reactance of 62.8 mega ohms. Essentially, it's an open circuit. So for transient analysis purposes, L shunt isn't even there. And we enable the transient analysis command and rock and roll. There we go. And you can see the initial oscillation builds exponentially until, in this case, it's passive stabilization, gain compression of the transistor begins to take hold and limit the amplitude. But now let's measure the admittance of the circuit that's seen across the inductor and look for negative conductance. We do that with an AC analysis, which we can reconfigure this circuit for AC analysis by setting L shunt to a very small value, 1 nanohenry, essentially a short circuit. We can't set it to zero. But now L1 has been removed from the circuit, but I can now measure the admittance at node VC by using this power supply as an AC voltage source for AC analysis and measuring the current that flows through this dummy voltage source, the ammeter branch VIM. Okay. And there I enable the AC analysis and I compute the conductance as the magnitude of I VIM multiplied by the cosine of the phase angle, and the susceptance as magnitude of I VIM multiplied by the sine of the phase angle of I of VIM. And when I do this analysis, here is the current flowing in the ammeter source VIM. It's 5.112 milliamperes at a phase angle of 93.8 degrees. The cosine of 93.8 degrees is negative. So at 1 megahertz, the network appears to have an admittance of minus 2.95 K in parallel with 812 picofarads. So the conditions for oscillation to begin and grow are present. That is that negative conductance. There you see it. Okay, so I would like to mention that at this point that I'm going to be making some of these resources available for your own use. Okay. But first, why did Gary and I start this One Human Lifetime project? A little background. Much of my early experience in electronics was with vacuum tubes. Now, this was junior high and high school. I have not worked with vacuum tubes professionally, but I did as an experimenter, as a hobbyist, as an amateur radio operator. And that made me rather unique among engineering faculty in the early 2000s of actually having worked with vacuum tubes, having had experience with them. I had a collection of historic electron devices that dated back to the 1920s, and from the late 1920s up to the late 1990s, a span of 70 some odd years, essentially one human lifetime. And when I retired, I wanted to leave that collection with my former employer as a permanent display. I thought that there would be real value in our students being able to see for themselves the tremendous progress that had been made in electronics within just a relatively short period of time. Unfortunately, it never happened. They liked the idea, but they couldn't find a place in the engineering building where the display would get a lot of visitors, but at the same time wouldn't impede foot traffic. And there was the expense of the case and itself, and was at work. They find that the money to buy a display case in the budget. And so, and they had other priorities, so it never happened. But I felt that there was still valuable history contained within these devices. So I recruited Gary to help with photography and graphics for videos to talk about the history of these devices. Gary is a talented photographer and graphic designer, but Gary and I met in the early 1970s as undergraduates at the University of Illinois, and we bonded over our mutual interest in amateur radio. We were both licensed amateur radio operators, and we still are. But so Gary also had a personal interest in, shall we say, old electronics, and he had worked with vacuum tubes, so we had that in common. So we were natural partners in this. And I also had a collection of articles and tutorials and examples that I had developed myself to supplement my lectures and to supplement the textbook. And I thought I would like to make these available. So oscillator-related resources that will be made available to you. There are tutorials and analyses in the form of PDF files. You're welcome to download them, read them, hopefully learn from them. The PowerPoint presentations that go in negative parts 1, 2, and 3, this one will be available. And LTSpice simulation circuits of the Colpitts oscillator, the Wein-Bridge oscillator, and the rather unique oscillator that I will show you on the next slide. And here it is. This particular oscillator circuit is based on a bandpass filter that uses a synthetic inductor that is realized with a circuit that's known as this generalized impedance converter. And the output of this bandpass filter is fed back into the input. And it's also fed back through across a pair of amplitude limiting diodes. And its transient behavior is, there it is plotted, transient analysis of that circuit. I leave it to you, if you're interested, to find the negative conductance that's present in that network. Okay. Resources are made available under the following conditions. Resources are presented without any warranty, implied or expressed. Gary and I put a lot of work into these, so please don't take our names off of them. The quality of what you get will vary. Some of the resources that you will find here, like the tutorials and so forth, were typed and they have very nice graphics and look very professional quality. Some of them were handwritten notes that I handed out in class, and some of them even, I admit it, contain cartoons. It's a work in progress. Materials may be added, removed, or reorganized at any time. And the link to the Google Drive folder where you will find these resources will be in the description attached to this video. Now, one note to make, the LTSpice simulations require you to have an installation of LTSpice. The good news is that LTSpice is free. It is supported by Analog Devices, which is the parent corporation of Linear Technology Corporation, which was the company that originally developed LTSpice. So you can download LTSpice from the Analog Devices website, install it, and then the simulations, you can run them for yourself. Okay? Comments and feedback are welcomed. The only thing I don't want are cease and desist letters and restraining orders. These are meant for interested people interested in electronics. These are meant for engineers. They're meant for technicians, hobbyists. And I would love to hear from, we would love to hear from folks like that, but we don't really want to hear from any lawyers. So, as always, thanks for visiting the electronic past with us. And I'm David Beams, and I will be seeing you again soon in another video.